After the ancient Greek mathematicians made amazing discoveries about curves, interest in curves declined for nearly 2000 years. But then, in the 17th century, curves became a hot topic of study again, leading eventually to the discovery of calculus. So what motivated the mathematicians of the 17th century to study curves after such a long gap? This is key to understanding the motivation for calculus, since calculus originated as a tool to study and analyze curves, and we can divide it into three main motivations: practical, theoretical, and philosophical. So let's start with the practical motivation. A major motivation for studying curves after such a long gap was discovering their practical value. See, historically, studying curves and geometry in general was considered an intellectual pursuit with little to no practical value. Apart from finding areas and volumes of the simplest of shapes, there wasn't much practical need for geometry, like finding the properties of an ellipse or a parabola, let alone the properties of more complex curves and shapes. And as a result, the focus in mathematics shifted towards more practical fields, like arithmetic, trigonometry, and algebra. But things started changing in the 14th, not the 17th century, when a link was discovered between the study of geometry and the study of change. Understanding this link will give us a better understanding of the practical applications of calculus. And to do so, let's start with a simple example. Imagine we have a wagon that's moving at a constant speed, say 10 meters per second. What distance does it travel in a given time? Say in 4 seconds. This question is easy. Since the wagon travels 10 meters each second, then in 4 seconds it travels 40 meters. But scholars of the 14th century were interested in a much more difficult question. They asked, imagine if the wagon speed is not constant, but is continuously increasing from 0 to some maximum speed, say 10 meters per second. What distance does that wagon travel in a given time? Again, say in 4 seconds. A group of scholars known as the Oxford calculators solved this problem using logical arguments. But shortly after, Nicole Orezm solved this problem using geometric arguments, and it is his method that interests us and that is related to the practical applications of calculus. Now, Orezm didn't explain how he came up with his method, but it is easy to deduce it. And to do so, let's start with the equation of speed. Now we say that speed is equal distance over time, which we can write for short as s equal d over t. And we can rewrite it as s times t is equal to d. This equation is exactly the same as the equation of the area of the rectangle. So if we take the speed as one side of the rectangle, Orezm took the height, and we take the time as the other side of the rectangle, then the distance would equal the area of the rectangle. This idea will help us solve the problem of variable speed. So let's see how. Before we solve our complex problem where the wagon completes its journey at a continuously increasing speed, let's solve a simpler problem where the wagon completes its journey at only 2 different speeds. So for example, at 5 meters per second for the first 2 seconds, and then at 10 meters per second for the next 2 seconds. The distance traveled in the first leg of the journey is the speed times the time, which is equal to 10 meters. And the distance traveled in the second leg of the journey is again the speed times the time, which is equal to 20 meters. To keep things more general and to reduce clutter, I will replace the numbers with variables. And since we assume that the duration of each leg of the journey is the same, which is 2 seconds in our case, we can drop the subscript from the time variable. Now, as we saw earlier, we can represent these two equations with rectangles. The area of the first rectangle represents the distance traveled in the first leg of the journey, and the area of the second rectangle represents the distance traveled in the second leg of the journey. We can bring the rectangles together, and the area of the resulting shape represents the total distance traveled by the wagon. Now we can repeat the exact same steps if the wagon completes its journey at 4 different speeds, in which case we can represent the distances with 4 rectangles. The height of each rectangle represents the speed of the wagon at that leg of the journey. The width of each rectangle represents the duration of each leg of the journey, which is now narrower since we divided the total duration by 4 instead of by 2. And the area of the resulting shape represents the total distance traveled by the wagon. And we can keep going on and on. The more we increase the number of speeds the wagon takes to complete its journey, the narrower the rectangles become, since we're dividing the total duration into shorter and shorter time intervals. And Oresme concluded that at a continuously increasing speed, the rectangles become infinitely narrow. That is, they become lines. The height of each represents the speed of the wagon at each instant in time, or what is known as the instantaneous speed of the wagon. And the total shape becomes a triangle, whose area represents the total distance traveled by the wagon. So, to solve our example, the final speed is 10 meters per second, which is the height of the triangle. The duration is 4 seconds, which is the base of the triangle. And the distance is the area of the triangle, which is half the base times the height, which is equal to 20 meters. And in this way, Oresme reduced the complex problem of finding the distance traveled by the wagon at a continuously increasing speed into the simple problem of finding the area of a triangle. And this gives us the first glimpse on the link between the study of change and the study of geometry. But it is important to note that the case we studied is a special one, where we assume that the speed of the wagon increases linearly. But this is not always true. For example, say that the wagon is going down and uphill. We say that the speed of the wagon gradually increases until it reaches a maximum at the bottom of the hill, and then it gradually decreases on the way up. And the speed lines would form a shape that looks something like this curve, whose area represents the total distance traveled by the wagon. In general, Oresme identified 3 different types of motion. Uniform motion, or motion where the speed does not change, and he represented it with a rectangle. We call this motion today motion at a constant speed. Uniformly deformed motion, or motion where the speed changes but it does so uniformly, and he represented it with a triangle. We call this motion today motion at a constant acceleration. Deformly deformed motion, or motion where the speed changes and it does so non-uniformly, and he represented it with curves. We already saw one example of these curves, but this category of motion includes any other types of curves. We call this motion today motion at a variable acceleration. But Oresme didn't limit his geometric method to studying motion only. He used it to study different types of change. So let's take another example. Imagine we're filling a glass with water at a continuously increasing flow rate. What volume of water would be in the glass after a given time? We can solve this problem by using the exact same steps we used in the previous example. And to do so, let's start with the equation of flow rate of water. Now we say that the flow rate is equal to volume over time, which we can write for short as R equal V over T, and rewrite as R times T is equal to V. We can represent this equation with a rectangle, whose height represents the flow rate, its width represents the time, and its area represents the volume. Again, before we solve our complex problem where we fill the glass at a continuously increasing flow rate, let's solve a simpler problem where we fill the glass at only 2 different flow rates, which we can represent by 2 rectangles. The area of the first rectangle represents the volume filled at the first flow rate, and the area of the second rectangle represents the volume filled at the second flow rate. And the area of the total shape represents the total volume of water filled. Again, we can keep going on and on till eventually, at a continuously increasing flow rate, the rectangles become infinitely narrow. That is, they become lines. The height of each represents the instantaneous flow rate of water, and the total shape becomes a triangle whose area represents the total volume of water filled. Once more, this is a special case which is not always true. For example, we can imagine that someone is gradually and randomly increasing and decreasing the flow rate of water, and the flow rate lines would form a shape that looks something like this curve, whose area represents the total volume of water filled. In general, a rhythm represented the instantaneous rate of any change with a line, whose height is proportional to that rate. The lower the rate, the shorter the line, and vice versa. He called the instantaneous rate of change the intensity of change. Over time, the intensity lines accumulate, forming a shape, which, as we already saw, would be a rectangle if the intensity is constant, a triangle if the intensity changes uniformly, or some sort of a curve if the intensity changes non-uniformly. Oresme argued that the sum, or what is known today as the integration, and what we've been calling in this series as the stitching of the intensity lines, which is also the area of the resulting shapes, represents the total amount, or what he called the quantity of change. So, for example, in case of motion, the intensity of motion is the instantaneous speed, the quantity of motion is the total distance traveled, and today we say that the integration, which is represented with this symbol, which is known as the long S for sum, or more accurately, the Latin word summa. So we say that the integration, or the sum, of speed at each point in time, dt, is equal to distance. I'll talk more about calculus notation in a later video in the series. In case of water filling, the intensity of water filling is the instantaneous flow rate. The quantity of water filling is the total volume of water filled. And today we say that the integration, or the sum, of the flow rate at each point in time is equal to volume. Although these terms of intensity and quantity used in this context are medieval terms and are not taught today in calculus courses, they're very helpful in building an intuition about the practical applications of calculus. And we can use them directly without the need of drawing narrower and narrower rectangles. So let's take another example. Imagine we have a solar panel that is charging a battery. What is the total amount, or quantity, of energy stored in the battery after 1 day? Now, to keep things simple, we will assume no energy losses. So the quantity of energy converted by the solar panel is equal to the quantity of energy stored in the battery. Now we say that the intensity of the sun's energy, or what is known as the power of the sun, gradually increases from sunrise until it peaks at noon, and then it gradually decreases until sunset. And the power lines would form a shape that looks something like this curve. And the integration of these lines, which is also the area of the resulting shape, represents the total quantity of energy generated. And since we're assuming no losses, it's the total quantity of energy stored in the battery. So by going back to our table, in case of energy, the intensity of energy is the instantaneous power. The quantity of energy is the total energy generated, or in this case stored in the battery. And the sum, or the integration of power at each point in time, is equal to energy. In the last three examples, we considered change that occurs over time. And although this is the most common type of change, it is not the only one. For example, Oresme identified another type of change, one that occurs over space. To demonstrate this, let's use the example of a rod with varying density, which is represented here with varying colors. Teal for a low density, and red for a high one. Now, density is the intensity of weight, and we can represent it with lines at each point in space along the length of the rod. And we say that the integration of the density lines along the length of the rod, which is also the area of the resulting shape, is equal to the total weight of the rod. So, in case of weight, the intensity of weight is the density at each point along the length of the rod. The quantity of weight is the total weight of the rod, and the integration of density at each point along the length, dl, is equal to weight. Today we consider change not only over space or over time, but over any other medium, be it temperature, pressure, current, voltage, frequency, and the list goes on. And this gives us an overview of the link between the study of geometry and the study of change. And we also saw how integration plays a role. But calculus is more encompassing. To see how, let's revisit our examples. Now we said that the intensity lines form shapes that look something like these curves. But this is vague language. we want to mathematically describe these shapes, or in other words, we want to find equations for the curves that envelop them. This is achieved by a branch of calculus called differential equations, a more advanced branch that's usually taught at university level in mathematics, physics, and engineering degrees. After we find the equations of the curves, it is time to analyze them and find their properties. And the two most commonly used properties are first the tangents to the curves, where we pay special attention to where the tangents are horizontal, as this gives us the points of maxima where the intensity is at its highest, or the points of minima, where the intensity is at its lowest. And we achieve this by a branch of calculus called differential calculus. The other most commonly used property is the area under the curve, which, as we already saw, gives us the total quantity of the thing that we are studying. And we can achieve this by a branch of calculus called integral calculus. But of course, calculus wasn't known at Oresm's time. In fact, Oresm didn't have the ability to study and analyze curves in general, and therefore he limited his studies to the first two types of change only: uniform and uniformly deform. The third type, deformly deform, had to wait for further development in mathematical theory. Which brings us to the second motivation for studying curves after such a long gap: theoretical motivation. Mathematicians of the 17th century were motivated to study curves simply because they could. Recent innovations of mathematical theory allowed them to study curves in ways that weren't possible to earlier mathematicians. See, historically, there were a number of obstacles that prevented mathematicians from studying curves. The first obstacle was the difficulty in generating them. We saw in the last video how the ancient Greek mathematicians had only around 12 curves to study. This number did not change much for nearly 2000 years, since it wasn't easy to generate new curves. Perhaps the only curve that was added to the mix during these years was the cycloid, which is the curve that could be obtained by tracing a point on a rotating circle. And due to this limited number of curves, mathematicians weren't keen to keep studying them. But things started changing rapidly in the 17th century after the introduction of a simple yet profound idea that made generating curves a very simple task. This idea was the XY plane, which was introduced independently by René Descartes and Pierre de Fermat. What made this idea profound was that it linked the two major branches of mathematics that were known at the time: geometry and algebra. And it made generating curves as simple as writing algebraic equations. So for example, this equation generates a parabola. This one generates a circle. This one generates a hyperbola. And the list goes on. So while the ancient mathematicians had only around 12 or 13 curves, after the introduction of the XY plane, mathematicians of the 17th century had an infinite number of curves. We can imagine how they must have been like kids in a candy store, with so many curves to choose from and study. The second obstacle for studying curves before the 17th century was the difficulty in analyzing them. Before the 17th century, the go-to method to analyzing curves was the method of exhaustion, which was a very difficult method to implement and could be only applied successfully to a limited number of the already limited number of curves. Now, the method of exhaustion was difficult to implement because it avoided the use of infinitesimals, which were considered an intellectual taboo that could lead to errors and logical fallacies. But things started changing in the 17th century after Johannes Kepler published his book, New Solid Geometry of Wine Barrels, in which he used infinitesimals to find areas and volumes of different shapes and wine barrels. Now, Kepler wasn't the first person to use infinitesimals, but he was the first one with authority to use them systematically and to publish a book about them. And this encouraged other mathematicians, especially younger ones, like Bonaventura Cavalieri and Evangelista Torricelli, to dare to use them, which opened up the door to new methods of studying and analyzing curves that eventually evolved into calculus. Now, it is important to note that infinitesimals were rejected again in the 19th century and were replaced with limits. They were rejected for the exact same reasons they were rejected in the first place. They lead to errors and logical fallacies, but they were an important step in discovering calculus. The third motivation for studying curves after such a long gap was philosophical motivation. Mathematicians of the 17th century were motivated to study curves because they speculated that curves hold the keys to unlocking the secrets of the universe. This was inspired by two major discoveries. The first one was by Johannes Kepler, who was interested in studying the motion of the planets and was convinced that they must follow simple geometric patterns. See, at the time, the accepted model of the universe was geocentric, where the Sun and the planets revolved around the Earth in complex orbits. Not only these orbits were complex, they were also inaccurate, and no one expected that this inaccurate complexity hides a simple truth. No one but Kepler. See, Kepler was a mystic, and he was driven by a deep belief that geometry provided God with a model for the creation. And he was determined to find that model. But Kepler was also a scientist, and he needed data to prove his belief. And he got access to such data when his mentor, Tycho Brahe, passed away, leaving him with more than 20 volumes of accurate astronomical observations where Tycho recorded the positions of the planets over the course of more than 35 years. But proving the belief wasn't easy. See, Tycho's observations were made from the Earth's perspective. But Kepler was a Copernican who believed that the Sun and not the Earth was the center of the universe. So he had to recalculate the positions of the planets from the Sun's perspective. Afterwards, he tried to find a model to fit the new data into. After years of trial and error, he eventually found what he was looking for. The planets, including the Earth, revolve around the Sun in simple, elliptical orbits. His mystical belief was correct after all. The second discovery was by Galileo Galilei, who was interested in studying the motion of objects here on Earth. He did many experiments. One of them involved rolling balls with different speeds over the edge of a table, recording how far they've traveled, and carrying out detailed calculations. After many careful experiments and calculations, Galileo discovered that the trajectory of a projectile, say for example of a cannonball, was not a straight line as was believed, but a curve, and not any curve, a parabola. The ellipse and the parabola, two of the conic sections that were studied in antiquity for purely intellectual purposes, were now at the heart of two major natural phenomena. What is the link between the cone, or geometry in general, and the universe? These and similar discoveries led Galileo to famously say, "The universe is written in mathematical language, and its characters are triangles, circles, and other geometric figures, without which it is impossible to humanly understand a word. Without these, one is wandering in a dark labyrinth." And a new age of inquiry, one based on mathematics and geometry, has begun. So, for practical applications, theoretical innovations, and philosophical speculations, curves became a hot topic of study again in the 17th century. And mathematicians were eager to study and analyze them, and they came up with brilliant methods that eventually evolved into calculus. These pre-calculus methods are the topic of our next video. See you then.